Hi, welcome back. In this lecture, I would like to introduce our first multi-qubit quantum gate called CNOT. CNOT is a rather important quantum gate. In the same way that the Hadamard gate was our gateway to superposition effect, the CNOT will be our gateway to the entanglement effect. So let's start and see more in detail what CNOT is about. Well, a CNOT stands for a conditional NOT, so it's basically a NOT operation that is executed on a condition. As I said, CNOT is our first example of a multi-qubit operation that requires more than one qubit to operate. In particular, CNOT is a 2-qubit operation because it operates on 2 qubits and can be thought as an if a condition programming constructs with the following condition. That is, apply the NOT operation to a target qubit, but only if a condition qubit has value of 1. In the textbook and in the papers, the control NOT gate is represented in the following way. So we have the control qubit that is represented with a dot, and then we have the target qubit that is represented with the operation we want to execute. So this is the target and this is the control. Let's see how this looks like in the circular notation. So we know that the NOT operation on the first qubit is just basically swapping these qubit pairs, so we just pairs. So in the case of the first qubit, the pairs are just the 2 by 2 neighbors, so we just swap. If we look at how CNOT operates in circular notation, is basically a NOT, but more limited to a certain pairs. So you see, the CNOT only operates on these two. We can see that the CNOT is essentially as the NOT operation, only more selective. Apply the NOT operation only to values whose binary representation, in this particular example, have 1 in the second bit. Right, so let's see this case. We have the target, that target qubit is the first one, and then we have the control qubit that is the second one. And then to help us to understand how this operates, we can just write the binary representation of this different state. So this is 0, 0, 0, 0, 0, 1, and then we have 1, 0, 1, and then we have 0, 1, 1, and then we have 1, 0, 0, 1, 0, 1, and then 1, 1, 0, and then 1, 1, 1. So we can see, for instance, that this NOT operation only operates on those pairs where the control qubit, that is the second one, is equal to 1. So we see here 1, 1, and then here we have 0, 0, so nothing, the same here, 0, 0, and then here 1 and 1 again. So this control NOT operation only acts on those states. So very similar to the NOT, but the way to think about the CNOT is just a NOT operation that is just very selective on depending on the value of the control qubit. It's also helpful to think CNOT as a tensorial form or matrix form. So in this case we have a 4 by 4 matrix or tensor, and then we have here the input. So we have our first state in binary notation, and then here we have the output state. This is representing a CNOT operation with the control qubit on the second and then the target qubit on the first qubit. As you can see, when the second qubit is in state 0, so this is 0 and 0, so the output is the same. So this here there is an identity matrix. When the control qubit is on 1, then we are having a NOT operation on those states. So if we have 1 0, then we will get 1 1, and then if you have 1 1, then we're going to have 1 0. Like the NOT operation, the CNOT is its own in inverse. That means that applying the CNOT operation twice will return a multi-qubit register, a 2-qubit register, to its initial state. So if we do this control NOT in place, I just do the swapping, you can see here that we have a 2-qubit system characterized by this complex number multiplying each state. Then we apply the control NOT, and in this case is on the second qubit. This corresponds to swapping the complex number of the second state and the third state. So we do the first swap. When we take this one and we put as input as an argument to another CNOT, and we see that the final results is actually the initial quantum system, the 2-qubit system that we were working on. This is the last slides, and talk to you soon. And we're going to see how to use the control NOT to make entanglement in the next lecture.